Good afternoon, everyone, and welcome to part 7 of the ASHRAE Ireland's COVID-19 mini-series. My name is Tony O'Keeffe, and I'll be chairing today's session. So here's the agenda for today's webinar. I will give a short introduction and cover some housekeeping and general information before handing over to today's panelist, Mr. Jarek Kurnitski, for today's topic, REHVA COVID-19 guidance for HVAC systems operation and reduction of the spread of viral diseases in workplaces. There will be 10 to 15 minutes for Q&A from the audience after the presentation. So just in relation to the questions and answers section, if this is your first time joining, I just want to highlight a couple of points. First of all attendees are muted by default, but if you would like to ask a question, please use the questions tab or the chat function to submit your query, and we'll do our best to answer it during the seminar. You can submit questions at any time during the seminar, but I would encourage you to get your answers or your questions into us as early as possible for us to be able to answer them. If you have any difficulty asking questions, or if you have any questions after the seminar, please do make contact with us using the secretary@ashraeireland.org email address provided. You can also access PDF copies of today's presentation in the Handouts tab using the GoToWebinar tool, and so it might be useful for you to download those, and they'll have a more detailed explanation of some of the slides. So lastly, when the seminar is concluded, you will receive a very short survey with 3 questions, which we would really appreciate your response on. It helps us to plan for future sessions and understand how well these seminars have been received. So in relation to this webinar series, it was launched as part of our response to COVID-19 in order to help disseminate expert guidance to our members. We also have a COVID-19 reference section in the ASHRAE Ireland website, where you can find further information. There's relevant guidance from ASHRAE and the likes of CTTC and REHVA, which are very useful. Recordings from the slides and from previous webinars are also available on the website, alongside with a series of blog posts and technical articles we've prepared to go along with this series. So it's an 8-part series, and it's been going fantastic so far. We've been very lucky with the quality of speakers we've had, and today it's no different. I would encourage you to look back if you've missed any of the previous seminars, to look back. There's YouTube recordings, and there is slides available. Our final speaker will be Brendan Reddington, and that will take place in 2 weeks' time on the 24th of September. So we're looking forward to that as well. So just in relation to some other resources that may be of interest to you, there's a lot of information regarding ASHRAE resources on the slide, but if you download the slides, all of these links that I provide will be live, and you'll be able to access any of that information from it. There's also a really useful infographic that is an excellent, I suppose, starting point to access any of the ASHRAE guidance and literature. We're covering a very broad range of topics, but specifically around COVID-19, it's an excellent place to start. So again, if you download the slides, this slide will be live, the links will be active, and you'll be able to follow it. Or if you go onto the ASHRAE website, you'll be able to find this. It's a very useful place to start. So there's also ASHRAE Learning. The ASHRAE Learning Institute provides an awful lot of training. Again, if you use the main ASHRAE website, you'll be able to find all those links. There's both free and paid training. So it's again, there's a very wide breadth of resources there. So now I'm going to hand over to today's speaker, Mr. Jarek Kurnitski. Jarek is a professor at Tallinn University of Technology, Estonia, and at Aalto University, Finland. As chair of REHVA Technology and Research Committee, he has been leading the REHVA COVID-19 task force, preparing European HVAC guidance for an epidemic situation. He is internationally known for the preparation of technical definitions for nearly zero energy buildings, and he has been deeply involved in work to improve the energy efficiency and indoor climate of the built environment in Estonia and Finland. So Jarek, I'm going to hand over to you as presenter.
Well, thank you, Tony. Thank you for this introduction, and I am just sharing my screen. Well, now my slides should be visible, and yes, my presentation is about REHVA guidance for HVAC operation. So this guidance is available in the REHVA webpage, and it has been prepared so that it is dedicated to HVAC systems, so how to operate the buildings and technical systems. And it's complementary to general guidance, for example, provided by WHO. This is already the third version of this guidance and has first launched already March 17 and then twice updated, and this development will continue. So next version expected within a couple of months. So mainly targeted to HVAC professionals, but also, let's say, for occupation and public health specialists, all those who make decisions how to use and operate the buildings. And its scope is limited very much to commercial and public buildings. So mostly it's dealing with measures what one can apply in existing buildings and existing systems, but there is also some discussion included for more, let's say, far-reaching actions and how to conduct risk assessment and so on, what would be important for the future ventilation systems and improvement of the ventilation systems. So I would like to start with some, let's say, basis. What are the transmission routes and what is important? So altogether 5 transmission routes have been recognized. However, first 2 of them are the most important. So we speak about close contact region. Very often it is, let's say, 1 or 2 meter. And to be more specific, we are using 1.5 meter because most of evidence applies for this 1.5 meter. And it could be defined so that large droplets exhaled by a person will settle down within 1.5 meter. When we speak about droplet velocity of 10 meter, initial velocity 10 meter per second, which is typical for coughing, and droplets smaller than 60 micrometers, they actually evaporate and desiccate before they will reach the ground, and then they can move longer distances. And the smaller the droplet, the longer the settling down, and air velocities will carry very well droplets which are smaller than 10 microns for a very long distances, and 5 micron practically does not have any settling velocity, so it's completely following the airflows in the building, in the space or wherever. So in that respect, this 1.5, let's say, meter definition is a bit artificial when we speak about the droplet size, but it's important because there is one-fold mistake in most of the medical literature. So medical literature is telling that droplets larger than 5 microns will drop down within 1.5 meter, and actually it's not 5, but it's 50 micron, and to be more accurate, it's even 60 microns. So it's a kind of like change what has happened to recognize these aerosol physics facts. And another even perhaps more important is the concentration in the air. And it is evident that closer to the source, so closer to the infected person, the concentration is the highest. And then in normally ventilated rooms, the concentration will drop, as this right side figure will show. And this 1.5 meter distance is an estimate where the concentration has reached a roughly constant value and will not more decrease when the distance will be increased. So this means that this close contact has a very good basis, and usually it's about 1.5 meter. Then you can expect that the concentration has dropped down, so that from 1.5 meter the concentration will be equal in in rooms with well-mixed ventilation. So while in this close contact region we speak about both large droplet and small droplet or aerosol-based transmission, when after 1.5 meter we speak about long-range airborne aerosol-based transmission. So it means only these smaller droplets can be carried by airflows in this region. And there are very clear means how to deal with these routes in practice. So for the 1.5 meter physical distance needs to be applied. So just one needs to avoid the close contact. And when this for long range airborne ventilation is needed to dilute the concentration. And when we speak about the surface contact, then indeed it's a hand hygiene what is needed. So this figure tries to illustrate how far droplets can travel before they settle down 1.5 meter by the influence of the gravity. And the left side figure applies if air velocity is quite low, 5 centimeters per second, and then we see that 50 microns, so it's roughly 1 meter distance traveled, and it has settled down 1.5 meter. But for instance, for 30 micron, it's already close to 3 meters, and especially long distances apply for 10 micron and 5 micron, which are almost horizontal lines in this graph, showing that settling velocities are very low, and these small particles can be carried by the airflows by very long distances. So what's the range of the interest of droplets when we speak about airborne virus infections? So it is important to understand that the virus particles are very small, about 100 nanometers, so it's 0.1 micrometers, but they are not naked. So when person will exhale respiratory fluid droplets, these viruses are inside of these droplets. And the size of these respiratory droplets is less than 1 micrometer, so perhaps starting from 0.5 micrometer, and then the largest ones can be larger than 100 micrometers. But 100 micrometers is a limit of the largest particle size that can be inhaled. So basically this range from 1 to 100 is the range what is under interest. When there is also, as the droplets are fluid particles, they actually evaporate, desiccate, and the diameter will change within this process. But this evaporation process is very fast. Even for very large droplets, like 50 micron, it takes only 2 seconds to evaporate and to fully desiccate. And for instance, for 10 micron droplet, it takes only 0.1 second to fully desiccate. Fully desiccated droplet nuclei still include some fluid, and the virus will stay active in the air for 3 hours, roughly. So that's the reason we don't speak about initial diameter, but we consider, and in the calculations it can be considered that the evaporation is an instant process, and we speak about equilibrium diameter, so the original diameter will shrink to about 1/2 or 1/3 what would be a final diameter. So it's only 30 to 50% of an initial diameter. So this is the basis of aerosol physics in the background of these, let's say, how airborne transmission will happen and how cross-infections will be possible. So ventilation is the main mean to remove virus-laden droplets, and this figure illustrates on the left side, if the ventilation is on, we can see that there is an infected person and small and large droplets close to infected person, and when in the room air, what is well mixed, there is much lower concentration. And indeed, extract air will remove these droplets from the room. On the right side, there is the situation where ventilation is off, and then we can see that the concentration is equally high everywhere. And this is indeed not wanted situation, because the exposure actually equals to the dose, and dose is proportional to the infection probability, and this dose is a product of the breathing rate, concentration in the air, and the time. So what we need to do is to limit the concentration, and this can be reduced by adding more ventilation. And another way to limit the dose is to limit the occupancy time. So for a short duration occupancy, always the risk is smaller, because suspectable person will receive a smaller dose. So ventilation is one mean how to remove particles from the room. So when we speak actually about outdoor air ventilation, because recirculation doesn't help here, we need really to replace the air. But other possible means are filtration. If there are room air cleaners with good filters, then it is also possible to remove the particles, or UVC is also possible for the deactivation of viruses. But indeed, in most common rooms always have a ventilation, so the ventilation is the most natural thing how concentration of virus-laden particles can be controlled. So this airborne transmission was highly debated in the springtime, and was first not recognized, for instance, by WHO, but then it was a long scientific debate, and there was evidence for SARS already from 2002-2003, so SARS-CoV first virus, what was airborne, and then more and more scientific evidence was received especially from super spreading events that showed that in the closed environments with minimal ventilation, so high number of secondary infections were happened. And when it became clear that especially in crowded spaces with poor ventilation, the risk is especially high. And it is also known from some of these super spreading events that the ventilation rates were very small. For instance, in this Guangzhou restaurant and Skagit Valley Choir event, outdoor air ventilation rates were as low as 1 to 2 liters per second per person, as a typical ventilation rates are 10 liters per second per person according to existing standards. And after this scientific debate in the spring, which ended with, let's say, it was open letter by more than 200 scientists to WHO, when basically all important organizations have recognized the importance of airborne transmission. And today we can say that this really has been recognized worldwide. When we look at engineering controls and ventilation, let's say, what is the position in the infection control of environmental risks, we will see that such a pyramid is commonly used, and elimination actually is not possible for common type of infection sources for this virus, because infected persons are virus sources and they cannot be eliminated. So this physically removing the pathogen is possible from the surfaces, but not possible for a common virus source, what is just an infected person. When the next important measure are engineering controls, and these engineering controls mainly apply for ventilation solutions, but also room air cleaners or UV treatment are similar engineering controls. What are the next most important solutions and most effective solutions? When they are followed by administrative controls, and this personal protective equipment like the use of a mask is at the lowest level, so being least effective in this classification of environmental risk control commonly used. When I am going to these practical recommendations, what have been prepared, and actually there are 15 items listed in this guidance, which will cover how the ventilation needs to operate, what to do if there is no mechanical ventilations, how to manage with recirculation and heat recovery equipment, what are, let's say, guidance for the fan coils and induction units which will generate room level circulation, and does humidity and temperature matter practically. So what are the questions with the duct cleaning? Is it needed or not needed? What's the role of filters, and how to conduct the maintenance work? And finally, how to make visible that the rooms will have adequate ventilation. So this IAQ monitoring is also indeed one important point. So basically what is recommended is to extend ventilation operation time and to keep ventilation in constant air volume operation mode. If there is demand controlled ventilation system, so these need to be switched over to constant speed operation to maintain nominal airflow rates during occupied hours. And it is recommended to start ventilation 2 hours before and also operate 2 hours after the building use time. When it is recommended not to switch ventilation completely off at night times and weekends, but to operate at lower speed. And there is more, let's say, detailed guidance how to do this in the guidance document. So key aspect here is that we should supply as much as possible fresh air supply per person. And exhaust ventilation also needs to be operated all the time because one transmission route is possible via the toilets, so-called this fecal-oral route, and it is important that the toilets will have a good ventilation. So all buildings do not have mechanical ventilation systems. Then it is very important that windows will be actively used and open for longer times. So at least for 15 minutes, if somebody will enter the room where some other group of people have occupied before. And indeed, this opening the windows is not so easy in the winter time, but currently in the spring and summertime, this is a good solution and also can be recommended to boost the ventilation in buildings with mechanical ventilation. However, when the ventilation depends on occupants, so how the occupants will open the windows and so on, then it is important to make it visible what is the ventilation rate in the building, and a best and the most simple indicator for that is just a simple CO2 sensor, which should operate as a traffic light, and it is recommended to set these traffic light values so that yellow will start from 800 ppm in an epidemic situation, and red will start from 1000 ppm. So if it is more than 1000 ppm, then one really will need to open the window or leave the room. And such CO2 monitors are recommended, for instance, for the classrooms, for the meeting rooms, but also can be used in open plan offices and so on if there are no mechanical ventilation systems in the buildings. When it is often asked, what is the role of relative humidity and temperature? So this really depends on the virus. What applies, for instance, for influenza virus does not apply for SARS-CoV-2. And SARS-CoV-2 has been tested for typical indoor temperatures and relative humidity up to 65% with very high virus stability at this already quite a high relative humidity. So we can say that for SARS-CoV-2, humidification and let's say keeping a moderate relative humidity from 40 to 60% will not be a solution. This will not reduce the viability of this virus. So basically, humidification has no practical effect when we speak about this virus. And the temperature indeed is something what you cannot much change because of a thermal comfort. And for the deactivation, very high temperatures. So there are a couple of examples like 37 degrees during one day or 56 degrees during 30 minutes would be needed for the inactivation of this virus. And it is known at but cold temperatures, so 4 degrees, the virus has been highly stable for 14 days. So the lower the temperature, the longer the virus will remain active. But this has basically no implications for, let's say, for air conditioning and for ventilation, because we just see that humidification has no practical effect, and temperature we should keep according to the thermal comfort requirements. So, so no possibilities to affect this virus by these environmental parameters. When in the buildings, we very often have heat recovery devices, and some of them can have some leakages and also carry over pollutants. And perhaps the most critical ones are rotors, so-called heat or energy wheels, where pressure differences need to be correct in order to avoid leakages, and also carry over transfer can be suspected for this type of heat recovery devices. We know from practice that correctly operating heat recovery sections should not have no more than 2% of a leakage. But if fans create higher pressure on the exhaust air side, the leakage can increase to the 20%, what is not acceptable. So pressure conditions, pressure differences across to these supply and exhaust side are very important to avoid excessive leakages, and indeed the seals are recommended to check that leakages can be avoided. What applies the carryover transfer? Because this rotating wheel, there is evidence that suggests that the rotors which have adequate purge sector practically do not transfer particles. And this transfer is just limited to the gas-based pollutants. So we know that they very well transfer tobacco smoke and other smells, but this does not apply for particulate matter. And this virus also classifies as a small particles. And it is also known that the leakage does not depend on the rotation speed. So basically there is no need to switch off rotors. And what needs to be done and what is recommended to be done are just the inspection of the rotors. So there is one example about pressure differences in such heat recovery section, and we see that the correct pressure direction is from supply side to exhaust side on both sides of the rotor. So basically what is recommended, and there is one specific annex in the guidance how to do this inspection, is to take a measurements of the pressure differences and also to estimate the leakage, and the leakage can be estimated based on the temperature measurements. So this can be easily done, and in every building this is not a big inspection. What is recommended to be sure that these rotors operate correctly. So when it's quite evident that central recirculation is something what should be avoided, but in some systems it's impossible to avoid because of heating and cooling capacity issues. And if not possible to avoid, then it is recommended indeed to increase the fresh air rate and then to improve the filtration. Basically, to completely filtrate these virus-laden particles, we would need a HEPA filters, but this is usually impossible to install a HEPA filter to existing system. So alternative options are installation of UV, so ultraviolet chemical irradiation lamps to the duct, or perhaps the most simplest installation is just to replace existing low efficiency return air filter with more effective so-called F8 filter, which is a minimum improvement what is recommended. And what's the reason why we use F8 class filters? So just standard good outdoor air filters are effective in the filtration is the particle size range, so the droplet size exhaled by the person you can see here. So it's mostly from 1 to 10 micron, where are the maximum numbers of the droplets exhaled. And F8 filters are already very effective for PM1, so starting from 1 micron range, where the capture efficiencies can be from 65 to 90% for PM1. So therefore, this will provide a reasonable filtration efficiency when applied to the return air filtering. It's not 100% filtering efficiency, but most of the particles still can be removed with such a common filters. When it becomes a bit more tricky when we speak about room level circulation, fan coils, split units or induction units. And here the important is that these rooms are also ventilated. So to have outdoor air ventilation is the first thing, and if not available, mechanical outdoor air ventilation, what indeed can be a case in many, let's say, just fan coil only or split only systems which are only applied for the cooling, no ventilation. When it's just active operation of the windows, what is needed and the installation of these CO2 monitors in order to make this availability of the ventilation visible. And we also know that fan coils typically have very coarse filters which practically do not filter smaller particles but may still collect some particles. And when the fans will be started to operate, then they can also release these particles. So for that reason, it is recommended if the fan coils are in common spaces, then it is better to keep them on continuously at low speed in operation. So when it is stable airflow through these filters and let's say resuspension, and then the release of the particles will not happen if operated so. And as we discussed already with outdoor air filtration, that basically it is not designed for the capture of the viruses, but reasonable efficiency is provided by F8 filters. But for the outdoor air, it does not have any importance because outdoor air is not the source of the viruses. So this also means that there is no need to replace outdoor air filters, just according to the regular planned scheduled maintenance. No specific additional filter replacement needs. And also it applies for the ductwork cleaning, no specific need for the ductwork cleaning. When we speak about the room air cleaners, so to be effective, they need to have HEPA level efficiency, and air cleaners with electrostatic filtration principles can also be effective. And when it is important, what is the capacity of the air cleaner? So the capacity needs to be minimum 2 air changes per hour of the room air to have adequate let's say, circulation through the air cleaner. And it is important to locate these air cleaners close to the breathing zone. And then indeed it's a specific issue for the maintenance personnel because especially when they replace the filters, these can have some active microbial material on them. So common respiratory protection measures are needed, including respirators for the maintenance personnel making these operations in the buildings. So this is basically a summary of these 15 measures, but finally I want to discuss some, let's say, risk assessment and other aspects what are important for the future ventilation systems. So it's quite evident that ventilation rates need to be high and do not recirculate the air. But then there is one more aspect what is not so commonly understood. So these are, we can call these as directed airflows. So individuals should avoid staying in the airflow coming from another person. And if air distribution is well designed and we have mixing ventilation with low air velocity distribution, such directed airflows will not be a case. But in some cases, for example, split units can generate very high air velocities, 0.5 meter per second or something. And when it is possible that these high air velocities, if they hit infection source, then they will propagate the virus spread. So this is indeed not so easy to address in existing building, but for the future design, this is something what needs to be considered. And it is often asked, do we have something to say about ventilation rate? What would be a safe ventilation rate per person? What should be recommended? This is actually the information we don't have. There is no good evidence on that yet. But what we know is that ventilation rate has been very low in these super spreading events. It's only 1 to 2 liters per second per person. And existing standards recommend 10 liters per second per person. And there is more, let's say, specifically described here below. When one will apply a category 2 sizing, when it is 1.5 to 2 liters per second per floor area, and will correspond 10 to 15 liters per second per person in, let's say, offices. And when we speak about meeting rooms or classrooms, when one should use about 4 liters per second per floor area, what will correspond 8 to 10 liters per second, if done according to existing standards. But we really don't know, would this about 10 liters per second be enough or not? So no direct evidence is not available yet. But some evidence is available from hospitals, which generally work very well during these pandemic conditions. But in hospitals, it's typical to have a ventilation rate about 40 liters per second per patient, and in isolation rooms even more. So when we speak about 6 to 12 air changes per hour. But also in public buildings, such high ventilation rates exist if designed according to the current standard. So take this 4 liters per second per floor square meter. This will correspond in meeting rooms and in classrooms about 5 air changes per hour, what is very close to the ventilation rates what have been applied in older hospitals. So for that reason, it is possible to calculate the probability of the infection. It's well known Wells-Riley model for that purpose, and this dose depends breathing rate, concentration, occupancy duration we already discussed, and when we need just to know what is a concentration in the room, and this concentration can be calculated with fully mixed assumption, or in the larger rooms, indeed, this full mixing will not be the case, when one can measure a concentration or to run a CFD simulation to know how the concentration will develop. And this is not mathematically complicated calculation. What is a question is the emission rate. So what is the source strength? And this is not very well known yet for SARS-CoV-2, but some quanta emission rates, so how many quanta per hour will be caused, are available in the literature. And we basically can say that this SARS-CoV-2 is quite similar to common cold. And there is a lot of data indeed available for the common cold and also for the influenza. So source strength of influenza is lower than for SARS-CoV-2. And for SARS-CoV-2, it very much depends on the aerosol procedure we are conducting. So when speaking and loudly speaking or singing, these are intensive aerosol procedures, and then the source strength can be very high. And also, if we are doing heavy exercises like a sport, then breathing rate is higher and the source strength is higher. So there are some examples of probability calculations, so the risk assessment in typical rooms, and we see that, let's say, risk is high in small rooms occupied by a couple of persons. There is a two-person office room showing the highest risk in this slide, and also an open plan office of 50 square meter, where ventilation rate is less than according to the standards, only 1 liter per second per square meter, when the risk is higher than 5% for 8 hours occupancy. But open plan office, 2 liter per second per square meter ventilation, and classrooms calculated with different ventilation rates show lower probability of infection than 5% for 8-hour occupancy. So these spaces are already reasonably safe. When it applies for the meeting rooms, once again, we can have 4 liter per second per square meter ventilation, but in small meeting rooms, so total ventilation rate per infected person is low and the risk is high. So the restaurant here seems to be the most safe, and also for the shopping, it's a short time occupancy typically. This is also low risk, and low risk also for large meeting rooms. So meeting rooms were designed for 20 persons and more can be treated as quite the safe spaces. And finally, I just show this one example of airflow initiated by the split device, and where index person is sitting in the table in the middle and is basically hit by this airflow from the split unit, and it was suspected that this air distribution propagated the spread of the virus in this case. But most likely this is actually not true, because the main problem in this restaurant was actually the lack of a ventilation. It was practically not ventilated room, and ventilation rate only 1 liter per second per person. So without the split, the end result would likely be very similar, but this has been recognized so much publicity with this restaurant because it's a well-documented case, and everybody knows now that these split units can propagate the spread of a virus. However, it is not often when mentioned, but the main reason was the lack of ventilation in these cases. But there are much more complicated situations, and we know that in many buildings, underfloor air distribution has been used, and especially these underfloor systems are problematic because we speak about the droplets, and droplets cannot settle down if we have a supply from the floor. And it is also a tricky situation for some displacement ventilation system. So generally, air distribution is very important to be controlled and to be designed in future buildings so that the virus spread will not be propagated. So to conclude, there are indeed very many possibilities to improve the ventilation systems in future, but already technology and solutions we have today are enough to keep buildings in operation if the ventilation is designed according to existing standards, and in many rooms, especially in larger rooms, infection risk will remain at reasonably low level. What regards the airflow rates, indeed, more ventilation is always better, but to dilute the aerosol concentration, the total airflow rate, liter per second per infected person, this is the one what matters. And with current infection rates, a common assumption, or let's say design assumption, should be that only one infected person will occupy the building or will occupy the room. So these infection rates are so low that the common assumption is only one infected person. So this makes large spaces ventilated according to the current standards reasonably safe, but smaller rooms occupied by fewer people and with relatively low airflow rates pose a higher risk even if well ventilated. So that means that in these smaller rooms, it only is safe to occupy by only one person. And another way to reduce the risk is to limit the occupancy time. So thank you very much. That was all from my presentation.
Jarek, thank you very much. That was excellent. And we have some questions here that I'm going to open up for you. So just to start, any special recommendations for dealing with rooms full of choir singing or pubs where people are shouting? There's obviously a high velocity of airflow. Do you have any recommendations for
that? So basically, indeed, it's let's say if somebody is staying in the airflow coming from an infected person, so this can propagate indeed the infection risk, and this has been a case also in some airplanes, and there are some documented cases, actually not for SARS-CoV-2 but for some other viruses from the history. So this is known, but this is something what you cannot easily change in existing buildings, and I think this is important for the air distribution design in new buildings and for the new future buildings. In existing building, what you can do, you can only assure that the ventilation rates are enough high, and well, it's impossible to switch off split units or fan coils because either you need a heating capacity or cooling capacity, and they are needed. So basically, we recommend to assure that these rooms are adequately outdoor air ventilated and to install these CO2 monitors to see that the ventilation will happen.
Okay, excellent. Another question. A previous speaker, I believe it was Dr. Stephanie Taylor, carried out research in relation to the effect of an RH range of 40 to 60 and how it can lower infectivity levels. and aerosol transmission. Do you have any thoughts around that, around her studies? Are you aware of it? And is there any evidence, or what evidence have you based your conclusions on in relation to RH?
Yes, relative humidity 40 to 60% is beneficial for instance for influenza virus, and when influenza virus will remain less time active in such a moderate relative humidity, but this has not been case for SARS-CoV-2, and for SARS-CoV-2 we know that about 60% relative humidity it has shown very long time staying active. So actually we see that we need to understand difference between the viruses, and for SARS-CoV-2 epidemic situation, so moderate relative humidity is not the solution. So
okay.
If somebody wants to humidify, indeed it's fine, but it will not have any practical effect. So this is also when we give a recommendation what needs to be done in the building. So I think it's not relevant to say that somebody will need to humidify to increase the thermal comfort, because yes, it can be beneficial for the better thermal comfort in the winter time especially, but there is no evidence that it somehow will help to fight against the virus. So it is important to concentrate and to focus to real measures, and when you need to apply more ventilation, when you apply more ventilation, then the relative humidity can be even lower compared to situation with less ventilation. But still, this is the wanted situation, that we have more intensive air change rate and basically no need to take care about the relative humidity. It's a secondary factor in this business.
Okay, excellent. Can you say more on the issue of displacement ventilation systems that are frequently used in lecture theatres?
This displacement ventilation system, what was the last part of the question? Frequently used where?
Lecture theatres.
Lecture theatres, yes. Yes, indeed, in such lecture theatres, this is a common solution, and it is when underfloor air supply basically, and this indeed will it will take a longer time for the droplets to settle down if there is a floor air distribution used. But I think in such rooms it's very difficult or even impossible to change the system. What can be recommended is just to keep a physical distance, and so every second seat, every second row to be occupied, to be in the safe situation, and then the ventilation rate will also be much higher per person. I think this is some evidence that has been received from office buildings and underfloor air distribution, and basically when they try to increase the ventilation rate, it increases the particle concentration in the air. So increasing the ventilation rate with underfloor air supply didn't help. So, and I think this is something we need to consider when we design new buildings or we design renovations. But when we speak about the theaters, large lecture rooms, there is likely no alternative for this underfloor air distribution.
Yeah, okay, excellent. You mentioned CO2 and the importance in relation to monitoring ventilation levels a few times. So Is this a good indication of virus concentration in a room, assuming there is someone carrying virus in the room? And what are the levels you'd recommend?
So this was about CO2, this question, yes?
Yes, correct.
Yes.
So is it a good indication of, sorry, go ahead.
Yes. So it is not so easy to monitor air change rate in the room. And especially in naturally ventilated rooms when airflows are not so controlled. So that's the reason CO2 is the only parameter which will indicate how much outdoor air ventilation is in the room. And indeed, the value depends on the CO2 source, so the number of occupants. And there can be a situation where occupancy is lower, and this is the reason we recommend very low value of the CO2 to use 800 as a kind of yellow traffic light value and 1000 ppm as a red value, because this is just the only easy indicator we have, and this is better than nothing. If rooms are normally occupied, this CO2 indicator works very well. So it really indicates what is the outdoor air change in these rooms.
That's excellent. Okay, look, we'll close up there now. I'm just going to take over, and any further questions we'll follow up with. So just to wrap up, so I won't cover all of these. Just to say thank you so much to our supporters, and Jarek, thank you again. It was fantastic to have you here, and thank you for taking time to speak with us. Obviously, with the supporters, with our sponsors, none of this could happen without them. And if you have any questions you want to follow up with, please email Daniel at secretary@ashraeireland.org. So thank you very much. We're going to close the webinar now. Thank you, Jarek.
Thank you. Bye-bye.